Hello and welcome, Mr. Johnson. And today, in this video, we're going to be talking about normal force. Normal force is also sometimes referred to as force normal. So if you see that in a textbook somewhere, force normal, normal force, they are the same thing. But in beginning this, we need to talk about exactly what is normal force. Well, we symbolize this as F sub n. Typically, that's going to be a capital N, but you can see it as a lowercase as well, as you see down there in that banner. But when we talk about force normal or normal force, this is the force that surfaces exert to prevent a solid object from being able to pass through each other. So that may not make a whole lot of sense. So let's take a look at this block that I've got sitting on this table. Right now, this block obviously is sitting still. What this means in terms of physics is that all the forces are balanced. Okay? Now, there's no force in the horizontal. If there were, then you would see it sliding to the side. So right now, no forces in that horizontal. As far as in the vertical, though, because I don't see any movement, that also means that forces are balanced out. And there's always going to be a force in the vertical. That force is due to gravity. And when we're talking about an object, that force of gravity we refer to as the weight. And weight is calculated as mass times the value of acceleration due to gravity. Many times you see this simply as mass times gravity. It's symbolized in equation form. This is W equals mg, where g is the acceleration due to gravity. That acceleration due to gravity at sea level is 9.80 meters per second squared. Now, if you're taking AP physics, you are allowed to use a value of 10.0 meters per second squared to be able to simplify that math. But make sure you check with your teacher or your professor as to which value they would prefer you to use. I'm going to stick with 9.80 meters per second squared because that is the standard. But when we're looking at this, we do have a downward force. And again, that is a force of weight, or weight is actually a force. So what this means is I've got a downward force. And if that were the only force that were acting on this block, then we'd see this block sinking in through the table. Now, the way that we represent that is through something called free body diagrams. So I've drawn this out, and what we've got is an idea of the table. We have the box, and then this dot, which is representing the center of mass. And we draw an arrow downwards, and that is our force of gravity, which equals mass times gravity, or again, our weight. Well, looking at this diagram, if that were the only force acting on it, then it would sink down through that table. But we don't see that happening. So what that means is there has to be some upwards force also acting on it. And that is that normal force. Again, the force that the surface, in this case the table, is exerting on this block to keep it from passing through that table, or the table passing through the block. So what we do in free body diagrams, instead of something like this, we would draw just a single, what we call a point particle, and that represents our center of mass. And then we'd have an arrow downwards, and that would be our force of gravity, or mg. Then to show that upwards force, or the force normal, we would draw an arrow, again, originating from that point mass, or the center of mass, pointing upwards. That is equal but opposite, and that would be our force normal. So our net force on this has to equal 0. In other words, what we're looking at is that force due to gravity acting downwards has to be equal but opposite to the force of normal, or force normal, acting upwards. That way, force downwards equals force upwards. I've got one in a negative direction, one in a positive direction, and when I add those up to get net force, that value is going to be 0. So we can take this again, this net force equals 0, because if I'm looking at a coordinate system where downwards is negative, upwards is positive, then what I have is that force of gravity in the negative, my force normal in the positive, and that net force is going to be the force of gravity plus force normal. And again, if gravity is in the negative and force normal is in the positive, and they're equal but opposite values, then they're going to cancel out to give us a net force of 0. And anytime you have a net force of 0, that object is going to be stationary, just like we see for this block. But this brings up another point. Does force normal always equal the weight of the object? And the answer to that is no. But before we get into that, a couple of other points. Okay? When we're talking about force normal, first and foremost, normal force is a contact force. And what this means is that for objects to be able to have a force normal or a normal force existing, they must be in contact with each other. If they're not in contact with each other, then I'm not going to end up having a force normal. So when I lift this off the table, because it's no longer in contact with the table, there's no longer a normal force acting on it between the block and the table. Instead, now with me holding this, there is going to be a normal force between the block and my hand. Okay? So it's always a contact force. The other important thing is that normal force is always going to be perpendicular to the surface. So in this case, my surface is this horizontal table. So force normal is going to act perpendicular to it. And this is extremely important when we get into the concepts of frictional forces and especially forces on inclined planes. Because when you're dealing with inclined planes, to give you a little preview, when you take that plane and you start putting it at an angle, we're still going to have a force normal that is perpendicular to it. So our x-axis actually does not always have to be directly along the horizon. We can take that and we can set it at an angle, and that angle is still our x-axis, and we still have a force acting perpendicular in the y-axis. So extremely important concept to always keep track of the idea that a force normal is going to be perpendicular to the surface of that object that object is sitting on. Okay? So getting back to this idea of, does force normal always have to equal the weight of the object? The answer again is no. So let's walk through that real quickly. So right now it's sitting still. But if I exert a pressure down onto it, if I add an additional downwards force, notice it's still not being able to be pushed through that table. Well, if I've got the weight of this block or the force of gravity downwards, and then I'm adding force, then overall I've got a much larger downwards force. But if that object is still stationary and is not being pushed through, that means my force normal also has to increase. So let's go back to free body diagram and take a look at this again. So let me clear this board. And now what I have, again, starting out, before I apply that extra force downwards, is I have that force of gravity acting downwards, but now I'm going to add an additional downwards force. So we're going to call this force applied, or F sub A. And the idea is that these two forces add up so that my net force downwards or towards the negative is going to equal apply plus that force of gravity. Well, when I push down on this, again, my net force has to equal 0. Otherwise, I would see it being pushed down through the table, and we don't see that. So what this means is now this has to equal, if these are both in the negative direction, it has to equal a positive force normal, so that when these two things are added up, I still get a net force of 0, which means as I draw out my force normal now on this, if I take into account force gravity plus that force applied. I'm just going to draw it directly on top of it. So I now have my net force downwards. My force normal has to increase to counteract it. So what we see is when we apply a force in the same direction of force of gravity, then my force normal is going to increase. That way, when I take my force normal plus my net force downwards, I'm still going to get an overall net force of 0. So right there we can see that force normal does not always have to equal the force of gravity. But this now brings up another situation. If I press down, I see force normal increases. So what do you think happens when I apply a force upwards, but these stay in contact? Well, again, we're going to see a change in our force normal. Clear this board. I'm going to show you. This is a spring scale. When you apply a force downwards on it, that scale is going to elongate. So if I hook this onto the block and I start exerting a force upwards, hopefully you can see at home that this starts to stretch, but this is still in contact with the table. And as long as it's in contact with the table, I'm still going to have a force normal between the block and the table. But now I'm exerting a force upwards while gravity is exerting a force downwards. And again, if that block doesn't move, then the force upwards has to equal the force downwards. So net force would be equal to 0. So let's see this in a free body diagram. So again, I have my box sitting on the table, force of gravity acting downwards. But now, in addition to that force gravity, I apply a small force upwards. Well, if I add these, I'm going to get something other than 0. And again, even when I hook this through and I start to lift, we see the spring elongate, but it's not lifting off the table. So what that means, again, is that my net force has to equal 0. Well, the only way it's going to equal 0 is if now my force normal plus my force applied equals my force of gravity. So in this case, what we end up getting is that the force normal plus the force applied, both in the positive direction now, has to equal my force of gravity in the negative. That way, when I take the sum of the forces upwards and I add them to my force downwards, that force of gravity, the net force is going to be 0 and this remains stationary. Okay? So force normal does not always have to equal the weight of the object. The main idea is looking at how these free body diagrams work, and that if I've got the force of gravity downwards and that object is not moving, then the force upwards must be opposite but equal so that their sum is 0 and I don't see any motion. Well, if I increase the net force downwards by, say, pushing down on an object, then I have to see force normal increase to a larger value to account for not just the weight of the object, but also the extra applied downwards force, so that when I add them up, I still get a net force of 0 and the object remains stationary. Conversely, again, if I start lifting this, then I'm going to see a force upwards due to the applied force, and then that force normal, when they are added, force upwards. That way, again, it stays stationary. So long story short, you push downwards on an object, you're going to see force normal increase. You start lifting up on it, you'll see force normal decrease. Okay? So this is a solid surface. But if you take into account something like a trampoline that's flexible, you set a heavy mass in that trampoline, and you notice that trampoline warps around it. What's happening there is that is not able to exert a large enough net or force normal upwards to counteract the weight or force of gravity downwards. So that object wants to sink through that trampoline, but it can't, because instead of just opening up a space and falling through, it stretches the trampoline. And as it stretches that trampoline, you get a tension force, and that tension force is acting upwards. And in addition to the force normal that the trampoline can normally exert, eventually you're going to have a combined net upwards force that matches downwards force due to gravity, and the trampoline is going to stop stretching. And you can see this by placing different masses inside that trampoline. The heavier the mass, the more the trampoline has to stretch, so that the tension force, applied force upwards, along with that normal force, lets out that force of gravity downwards. The lighter the mass, the less it has to stretch. So this is all about a balancing of forces, and key idea in this, again, if you do not see motion on an object, like right now, this means that all forces equal zero. The forces in the horizontal as well as forces in the vertical. The horizontal forces are pretty simple. The vertical ones is where you have to take into account this force normal. So hopefully all of this has made sense to you. If you have any type of questions or anything like that, please remember to just leave a comment for me, and I'll get back to you as soon as possible. Also, don't forget to subscribe for future videos. And if you have ideas for future videos, please leave those in the comments as well. Just let me know, and I'll see what I can do. Thanks, and as always,